Okay, hey everyone, thanks for joining this afternoon for today's live stream. Today I'll be going through porting a simple Fortran application to GPUs using AMD's HIPFort. I'm Joe Schoonover with Fluid Numerics, and let's just go ahead and get started. I've got a few slides for us just to make sure everyone's on the same page. So first, if you have not programmed GPU systems before, this slide is for you. There's a couple things to keep in mind when you're on a GPU system. So what I'm showing here is a simple diagram of a very simple system. So we have a single CPU socket here on the left. That CPU has its own memory space here, which is the CPU RAM block. And then on the other side here, we have a single GPU. The GPU is connected to its own memory space. So you have these two distinct memory spaces, one for the host or the CPU side and one for the device, the GPU side. Now all communication, so this includes things like issuing instructions for things to run, moving data around, that happens over what's used to be a PCI bus. It's called PCIe switch, a PCI Express switch these days. There's also more exotic hardware, out there like Infinity Fabric, NVLink, these kinds of things. But the key thing to take away here is that there is a physical device on the motherboard that connects the CPU to the GPU. And typically this device is the slowest connection in this whole system. So if you consider the idea when you want to do a compute operation, you have to move data from the CPU RAM to the CPU if you're doing compute on the CPU side, and that takes some amount of time to move that data around. If you're on the GPU, same kind of deal. If you have data in the GPU RAM space and you want to do compute on that GPU, you have to move that data from memory onto the chip so that you can do the compute operation. And of course, when you're running your program, everything starts on that host side, and at some point you have to migrate your data to the GPU, and you got to cross this really slow connection. So ideally, you're touching this, very minimally, only when needed, typically at the beginning of execution, or you're somehow overlapping some data transfer with compute. But this is a key takeaway here I want you to have from this slide, is that there are two distinct memory spaces, and at some point during the program execution, we're going to have to manage pointers to data, both on the host side and on the device side. And then we'll talk a little bit about today how to run some kernels over there. On the right here, I have a diagram of, it's a rough diagram that's meant to encapsulate some key elements of the GPUs. Now each vendor has their own lingo for all these components. Today I'm going to be using AMD's language for describing these components. So at this sort of macro level, what you have on a GPU is, of course, you have that GPU RAM. You have what's called a command processor. The command processor is going to receive instructions specifically for executing kernels from the CPU, and it's going to divide those workloads that are sent across into smaller chunks and distribute those workloads to each of these what are called compute units. In the NVIDIA hardware, these compute units are referred to as streaming multiprocessors. The command processor is called a workload manager. Now on each of these compute units, there is sort of like a micro architecture or another layer of architecture that's available. So you have yet again another workload manager, or on the NVIDIA GPUs, these were called warp managers or warp schedulers. I think actually on the AMD cards, these are called wavefront schedulers. And then you also have a high bandwidth, very small relative to like the GPU RAM cache memory. Some people will call it L1 cache. On the AMD GPUs, it's called LDS, or local data share. memory. This is also called shared memory on the NVIDIA GPUs. And then you have some type of collection of register files. This would be like for vector registers or scalar registers. And then a collection of compute cores. Now the key takeaways here, and for the stuff we're going to be talking about today, because today is meant to be just like a beginner introduction to GPU programming using HIPFort, what you need to keep in mind is sort of, one, we have distinct memory spaces, so CPU memory, GPU memory are distinct. We have to manage those things separately. And we have API calls to manage that. And then on the GPU, there's sort of this view of a macro, a large scale version of the parallelism, so at the compute unit level, and then you have a number of compute cores inside of those compute units. So you have this sort of micro parallelism. So you have this grouping of, you have sort of this grid of compute units, and inside of that grid of compute units, you can launch multiple threads. So keep that in mind, because that will be coming up as a theme in the HIPFort and HIP programming models. Let's go ahead and go to the next slide here. So let's first talk about managing memory. I'll say it again because it's here. We have two distinct memory spaces to manage. You probably already know how to allocate memory if you've done Fortran programming before. On the CPU side, just using the allocate call, using allocatables or Fortran pointers, or you can, declare arrays if you know their size, at compile time. But we already know how to handle allocating memory here. If you want to allocate memory on the GPU, you can use the HIP malloc API call, which comes with HIPFort. What you'll pass in is a pointer. So this could be a Fortran pointer, or if you use the ISO C binding library, you can use the type C pointer. So either of those are possible here. And then you'll also pass in the size. So you don't need to declare the type of data in Fortran. You just need to declare how many entries in this array there are. So if you're doing multi-dimensional arrays and you have an n by m by p matrix for some reason, you would put n times m times p here. The output of the HIP malloc and all the HIP API calls in Fortran are going to be an integer error code, which you can choose to handle yourself, or as we'll do in the example today, you can use provided. It's the HIP check call. It will help you decode those errors, and the basic HIP check will kill your code if you run into an error. So there's some options there. Now, if you want to move data between CPU and GPU, so suppose you may have written some code on the CPU side, you're reading in something from file, or you've initialized an initial condition for some CFD code, or whatever it is you're doing, you need to then take that initialized data on the CPU, and if you want to compute with it on the GPU, you got to copy it over there. So you can use the HIP memcopy API call to make that happen. Takes in 4 arguments. The first one is a destination pointer. Again, this can be a Fortran or a C pointer. The source pointer, again, Fortran or C pointer. And then the size, so the amount of data you're going to move. Again, you don't need to include like the number of bytes in there, so this is really just the sort of number of elements in your array or your multi-dimensional array. And then you have this enumerator. Now the enumerator is just something that it's a variable that's provided with HIPFort and HIP that just indicates the direction that the data is going to go. And we'll look through an example here on the next slide that will hopefully clear that up. And then when you want to deallocate data at the very end, you can call HIPFree and again pass that pointer. So those are the 3 main functions we're going to work with today when we create data on the GPU, when we copy things around. We'll be working with these 3 API calls today, and again, it's really just to manage the fact that we've got a CPU memory space and a GPU memory space to keep track of. Now launching things, launching GPU kernels with HIPFort, it kind of is a throwback to the old days when CUDA was just getting off the ground, where you basically would write your HIP kernels in C, you would write a wrapper function in C, and then you would bind that wrapper function to Fortran using a Fortran interface and the ISO C binding library, thankfully, we have nowadays, makes that connection a little bit easier. So you're doing some language interoperability here. So I'll walk you through this in a very, very simple example, and then of course we'll get into the code lab and code it up live here. So the first thing, right, so there's 3 ingredients to do this. We need to write the HIP kernel. We need to write the launch wrapper that launches the kernel, and then we're going to expose that wrapper as a subroutine interface in Fortran. So 3 ingredients. Let's take a look at what that looks like. Oh, first, writing HIP kernels. So when you write a HIP kernel, you can, the typical types of things you're trying to parallelize are for loops or tightly nested for loops, usually. And what you want to try to do is express, rather than writing out maybe all the for loops and doing everything sequentially, is you can think about using thousands of threads at a time to execute subsets of those for loops. So maybe your for loop size shrinks a little bit. But when you're doing this, you need a way to sort of address your way through memory using the thread IDs. The HIP API gives you a few built-in intrinsics that allows you to calculate. Remember this sort of macro and micro view of the parallelism here. You can calculate your thread ID on the GPU. So what I have in the picture here on the left is just a depiction of like a 1D grid of threads. And that grid of threads is grouped into blocks. So it might be a little hard to see, but we've got this light gray grouping here. There's those 4 threads in this group, 4 threads in this group here. So this group here we would call block ID 0. This darker one here next to it would be block ID 1. This would be block ID 2, and so on down the line. Now within each of those blocks, we have the local thread ID. So we have 0, 1, 2, and 3. And then that local thread ID counting starts over again. 0, 1, 2, and 3. 0, 1, 2, and 3. You get the idea. To get that local thread ID, we use the thread IDX .x intrinsic. Now if you're doing multi-dimensional indexing, you can do .y or .z. But that's how we get that local thread ID. If we want the block ID, it's going to be block IDX .x, again, y or z if you're doing multi-dimensional. And then if you want to know the number of threads per block, that's going to be stored in block dim. So you can do some very basic things to calculate like a global thread ID if you wanted to, but essentially the idea we're after here is using the threads to access specific spots in memory that we want each thread to be working on. The last one we have is that we're going to be looking at today is the grid dim. It's the number of threads in this whole block or this whole grid of threads. So griddim.x would tell me how many threads I have in the x direction. .y would tell me how many I have in the y direction, and you get the idea. If I do .z, it's going to tell me how many I have in the z direction. We're going to use this as a way to change how we do things on the GPU, because we basically, instead of doing lots of iterations of a for loop, we want to basically each iteration do a whole bunch of threads accessing a whole bunch of data at the same time. And I'll show you what I mean by that. So on the left here, we're going to look at a very simple example, and then we'll dive into the code lab. So here we've got some really simple CPU code. We've got 3 one-dimensional arrays, A, B, and C. I'm going to make them a size of 1,000 here, just for the sake of making this easier to talk about. We're going to allocate those guys, and then maybe we do some initialization, and then we're going to add elements of A to the elements of B and store them in C. Right? So this is just a serial loop from 1 to n. Take AI, add it to BI, store it in CI. Okay, very, very simple. Now if we were to do this on the CPU, I'm going to walk you through everything that's on this right-hand side. So let's first look just at the top of this C code. So first we have the HIP runtime library, which is going to be there, so that we get access to the intrinsics we need for the for block IDX and etc. Now instead of doing sequentially 1 to n, what I want to do is, let's say I have thread 0 we'll say thread 0 does A1 plus B1. I have thread 1 do A2 plus B2, and so on down the line. And if I only have 100 threads available, what I want to do is have the first thread now pick up at index 100, and then thread 1 would do 101, thread 2 would do 102, etc. So if I have threads that so if I have a certain number of threads, sorry, this should just be grid dim up here. So what I basically want to do is have each thread do a strided loop rather than a sequential loop. But each thread is going to start at an element that's given by its own thread ID. I hope that made sense. So what we're going to do first here is we're going to calculate. So at the top here of this, so this is the HIP kernel. I'll back up here. So this is the HIP kernel. We have it declared as a global type. You need to have this global type. Oops. We need to have this global type specifier in the kernel declaration. This indicates to the compiler that this kernel is going to be run on the GPU, but it can be launched from either the GPU or the CPU. Give it a name, and we're going to pass all of our arguments as pointers. And then, of course, every global GPU kernel is going to be of type void, so it's not going to return anything. Now, this first line here, what we're going to do is calculate that global thread ID. So if I know my local thread ID, I know which block I am in, and I know the size of that block, I can calculate my global address in that thread space. Right? So that's all this first line is going to do for us. The stride, and I apologize, this should just say griddim.x, so it's the total number of threads that are available. And so what I want to have each thread do, it's going to start at its own thread ID, it's going to go all the way up to n, and it's going to increment by stride rather than by 1. So I'm doing far fewer iterations per thread, but now I have however many threads I launch with running the same code multiple times. So if I have an array of size 1000, I have 100 threads. Each thread's going to do a loop of size 10, and it's going to do them, sort of in unison with each other in some sense. So that's what that kernel's doing. We're going to be looking at another example where we're going to be doing a stencil code here, so we'll be writing another kernel. Looks very similar, but of course for a different operation. And now we have, in Fortran, we need to do what's called the kernel wrapper. So we're going to start a void function. It's going to be declared in an extern C block. This is needed so that the name of the symbol for this function is not mangled by the compiler. And this is kind of important because when we want to bind this into Fortran code, we can't have name mangling. And what name mangling means is what the compiler is going to put if I don't declare this in an extern C block. In the object file that's created when you compile this code, you're going to have vec add wrapper and then some sequence of the arguments like sort of appended to that name. If I declare in extern C, the name of that symbol is simply going to be vec add wrapper, and it's not going to roll in any of these arguments into that symbol name. So kind of important that we have that. So here I'm actually going to have this one set up to pass the grid and block size for launching that kernel. So the number of threads per block, the number of blocks in that grid, and then we'll pass in our arguments. And then to launch, if you've done CUDA programming before, this looks familiar, but if you haven't, I'll walk you through this. This is what's called chevron syntax. Here, so we have the name of the function. In the chevron syntax is where you're going to basically tell the GPU how many threads you have per block. That's over here, and then how many blocks you have in that grid. And then we'll just go ahead and pass our arguments right across. So there's the first two ingredients. We have our kernel. We have our kernel wrapper. The next bit is, of course, on the on the Fortran side, we'll need to actually bring in the ISOC binding layer. So let me walk you through a couple things here. So first, if you've been working with allocatables in Fortran, you will need to switch over to using the Fortran pointers, even for your host data. That's needed really to be compatible with the HIPmemCopy API. So here I've got my host side data, A, B, and C are now pointers rather than the allocatables that they were before. And I've got Fortran pointers for my device arrays, and I'm going to initialize them to null. Now, HIP-malloc with Fortran is quite nice in comparison to HIP-malloc in C, because you have these other optional arguments. So after we've allocated our host side data, we can use this optional argument. It's called mold. What mold allows us to do is use the host side data as a mold. If you've ever done like resin casting and that kind of stuff, that's kind of like the same thing. The host data already is sort of a model for how the data should be. So we use that model, or the mold here, to tell HIP-malloc how much space to allocate for DA, or the device copy of A, on that device. So that's what we're doing here. We call HIP-malloc, and here's that HIP check module I mentioned before. We do the same thing for B and C. Allegedly in this little set of ellipses, we've done some initialization for A, B, and C. So what we want to do before we do our vector addition is memcopy. Our destination is DA. Our source is A. The amount of data is N. We have N entries in that array. And then here's that enumerator, HIP memcopy host to device. Of course, you could imagine going the other way. It's just going to be HIP memcopy device to host. So we got that for A and B. And then down below, I'll go ahead and remove myself here from the picture so you can see the rest of this. We have vec add wrapper. Again, we pass grid block. And when we do the tutorial, you'll see how these are specified. And then we pass, this is crucial, when you go to launch your kernels, they have to be C pointers. So we have to use the cloc intrinsic from ISO C binding to convert those Fortran pointers to C pointers. So A, B, and C here converted to a C pointer. Hopefully I have. Let me see, did I exclude it for some reason? I must have. I guess we'll get to the Fortran interface when we actually do the code lab. Now the code we're running today, it's a stencil code. I didn't have this in the last video, and we were working with the same code, so I figured I'd show it this week. Essentially what this code is going to do is we have this 2D grid, so I and J, and to get the value of a grid point at a future time slice, at a future step in time, we're going to take the this like 9-point stencil. So I actually think I have it a little bit bigger in the example we're going to work with, but you get the idea. What we'll do is we'll take the nearest grid points centered around this central point, average them with some weights, and I think we're using Gaussian weights for this one, to get the new value. What this essentially does is smooth out some data that you might have. That's really all it does. This is a very common pattern you see in codes like stencil operations of finite difference, finite volume, these kinds of things, people who are doing Poisson solvers, stuff like that. This stencil is ubiquitous. It's everywhere. And the way it's written up typically is we'll have, I guess this is one way, I've seen it done quite a bit, is you'll have a 2D array for your data, and it goes from 1 minus some ghost width, or the width of your stencil, up to n plus the width of your stencil. So, really the points we care about are on indices 1 to n, and then 1 to m, but we carry these sort of ghost values around so that we can apply things like boundary conditions, stuff like that. Then we have our weights, which are very small in size, so OL, minus OL to OL. Here that would be like minus 1 to 1, minus 1 to 1, because we're sitting around that central point. And we accumulate the product of the data with the weights and store it in a new variable. So we loop over each point, I and j, from 1 to n, 1 to m, and then we do this sort of reduction over this tightly nested loop inside. This is the guy we're going to be focusing on quite a bit today. So let me go ahead and change gears here and get into the code. Okay, so here we are on ORAM. This is our MI25 system here, MI50 system here at Fluid Numerics. So you see we've got 4 GPUs that are up and running, and we're going to be starting today. If you look down at the description of the video, there's a couple links for you to the Scientific Computing EDU GitHub IO site. So it's got some documentation that we're actively building out to teach you guys how to do GPU programming, but there's some code labs available. The Code Lab link is in the description in case you want to follow along on your own system, or if you just want to kind of use that as a guide here. Okay, so the first thing we're going to do is clone the repository. Now, I think I've actually already cloned it, so let me go ahead and kill this version because I don't want to cheat. Though cheating can be good in some situations. I was always told, if you don't learn to cheat, it's kind of hard to be a good researcher. There's a lot to unpack there. What we're going to do is clone from GitHub, Fluid Numerics, Scientific Computing EDU. Okay, so we're going to go into that. Let's go to samples, Fortran, and there's a few in there. We're going to look at the smoother example today. All right. Underneath there, if you did want to cheat, you can look at the final solution here underneath the source HIP directory, which is totally fine. What we're going to do, though, is start from the CPU-only serial version with source directory, and I'll show you how we get to here. If you missed last week's, you should check out last week's video for sure. We walked through doing the same exact code, but getting it running on the GPUs using OpenMP. It's quite fun. All right, let's go into that source directory and take a poke around. I'm like, part of the reason I like to do these videos is to not just teach you GPU programming, but to highlight a process that you can use if you're assigned the task of porting an application from one system to another. Not just GPUs, any system. The idea here is often, you're given a piece of code you may not know much about. And you got to figure out what's going on in there and what you really should be focusing on. So a lot of the technique that I'm going to be walking through, this overarching process that we're going to do, could be applied to these situations. Okay. Typically, every system has some kind of make system. So either CMake, so you look for like a CMake list.txt file, autocomp, so like an autorecomp.ac, or a configure script, those kinds of things. Or in this case, we have a simple make file. Okay, so minor distortion of the audio. Let me go ahead and drop that down. Thank you for telling me. Alright, hope that helps. I did just go ahead and drop that down. Alright. So, we're going to look at this make file. Take a look at what's going on here. Very, very simple. At the top, we've got a Fortran compiler defined FC. Now, I did write this code, so I kind of know what's going on. So that'll, of course, be helpful for getting through this. We have right now we've got the F flag set with no optimization. And importantly, when we start, it's a good idea when you're starting with the code to get a profile to understand where you're spending a lot of time in the application. For serial applications, this is quite easy. You could use the GNU prof, which you can enable the generation of those profiles using the -PG flag on most compilers. And then, of course, you can use the GNU prof command line tool to generate a hotspot and a hotspot profile and a call graph. So we'll walk through that first. That's usually where you want to start, because that's going to tell you what parts of the code you want to drop on the GPU first. Okay. For codes that have like MPI and stuff like that, if you're doing a GPU port for the first time, it's best to go ahead and just like try to come up with a demo or some flavor of the code that you can run that only requires one MPI rank. Because kind of diving in head first with like MPI plus GPU is absolutely insane. Some people can do it, but it's really, really hard if you try to just bite all that off at once. So that's where we're going to start. All we're going to do is build the code and try to understand how to use it. Now you'll notice this author, me, did not write a README, which doesn't tell me how to run the code, how to use it. So we're going to need to figure that out. Let's go ahead and run make. Okay, so we can see from the make commands it did create an application. You can tell it's an application. There's no -C flag, so it's not creating object files and stuff. -O, smoother. Of course, if we lsltr, you'll see the newest stuff down at the bottom. We got smoother. So if I just try to run this, alright, there's where my documentation is. Great. Somewhere code author should have some documentation for telling you how to use the thing. Looks like it takes in 2 arguments up front, so the number of grid cells in the x direction, number in the y direction, and then the number of iterations. So that's what we'll do. Now, when you're picking a benchmark problem, especially when you're doing porting activities, you really ought to pick something that exercises every bit of the code you want it to. And it should exercise it long enough to where you get a good, like, statistically stable representation of those routines runtimes, right? That's kind of like, you want to have something you can trust. Also, the other side of this consideration is you're going to be making typically a lot of modifications, and you don't want to be waiting hours and hours and hours for code to finish running to determine if what you did is still correct, if it runs fast, etc. So finding a healthy balance there is good. For this type problem, for a stencil problem, I'm actually going to do something fairly small. It'll only take a few seconds because I'm doing the live stream. That's my constraint. I'm actually going to do, I think in the code lab, I have 1,000 by 1,000 for the grid. Make sure I got that right. And we're going to do 100 iterations. So it's going to call that smoother 100 times. So we'll do 1,000 by 1,000, and we'll do 100 iterations. Now, whenever I do things in the future, when I make changes to the code, we're going to use those same exact parameters, because if I want to compare runtimes down the road, it's important to make sure we're still running the same thing, right? Okay, so I have a few new things that were created. I've got this function.text, this smooth function.text, and then we've got this gmon.out. Now, I know this gmon.out comes from the -pg flag being enabled. It's what we're going to use to create the profile, and then we'll take a look into finding out what these are here in a minute. Alright, so to look at that profile, we can use gprof. You'll pass the path to that binary that you ran to create that profile, and then you'll pass gmon.out. Now, what I need to do actually is go ahead and put that into a text file, because I want to compare. When we do profiles later on the GPU, we're going to want to compare the kernel, runtimes. Okay, well, let's take a look at that gprof.text. Very, very top, we've got, it's not a big code, surprisingly. I mean, the point was not to do a big code. The point was to show you some very, very basic stuff. We have 90% of the runtime, which is the percentage of time spent of the overall application, is shown in this left column. 90% of that, 97% of that runtime is spent in a method called apply smoother. Now, if you've done Fortran, this mod means it's in a Fortran module, so we know we're going to be looking for a Fortran module that has a function named apply smoother. Next down the line is this guy here at 2.77%. Reset F, again, defined in a Fortran module. So if you are porting to a GPU in general, what you'll do here typically is take the most expensive kernel, start with that, move that over, reevaluate, and kind of work your way down the hotspot profile that way, moving data over to the GPU as you need it. Okay, so that's our profile. Now later when we compare runtimes, you can compare the overall runtime of your application before and after porting. What we're going to do is compare this column here as the self second. So here I've got, of course, no optimizations. 9.84 seconds in apply smoother, and 0.28 seconds in reset F. If I wanted to be a little bit more fair, maybe I should change the optimizations. I don't know why I have C flags in here. We can kill that. So this is what I'll do. Let's remake that, and then let's redo the profile. Build it, run it again, and then we'll do another profile. Just we have two sort of reference points from where we started. Okay, so let's do this gprof. Command again, and this one we'll do minus 003, because that was 03 optimizations. And let's take a look at that. Okay, and then we'll do a vsplit Okay, so if we look, I mean, that's a huge difference, right? Just from changing the optimization flags, we go from 9 seconds for our apply smoother method to, if we look on the right side, the same line, 1.68 seconds. It's huge, right? So, you know, it wouldn't be fair for me to compare the no optimizations on the CPU with the GPU. And in reality, it's really not fair to compare a serial code on the CPU with a GPU accelerated application. Ideally, you know, if you want to know if it's worth it that you're on the GPU, what you should do is parallelize that code on the CPU and see if you can squeeze out all the performance that's available on a CPU. Of course, if you're just gung-ho about being on GPUs and you want to, you can do that. But if I have a lot of people who come to me and ask Joe, is it worth it being on the GPU? And typically that's my response. It's like, well, what's the best possible runtime you can get? A good rule of thumb, you can imagine a scenario where you've done everything perfectly on the CPU. I would take this number, 1.68, and divide by the number of cores that are available. In reality, that's likely the best thing you're going to get. On this system, I've got 16 cores, so 1.6 over 16 is like 0.1. So I would expect to maybe do this in 100 milliseconds. That's kind of what I would say. If I can run faster than 100 milliseconds, then I know I've done it. In reality, we usually don't do that well in terms of scaling efficiency for like multi-threaded applications. So, you know, you can kind of take it for what it is. Point being, if you want to know if it's worth it, always think about what you can do on the CPU side first. All right, so we've got code running. We've got profiles out. We have some files that were generated. So these function and smooth function.txt. These guys, if I grep around for these, so you grep is very helpful. If you don't have like a fancy IDE, I do, but of course when you're on like HPC systems, a lot of time you just have the command line. Grep is very, very helpful for digging around for things. So if I do grep function, and I just look at start.f90 files, I see that the main method actually opens two files for writing, right? I got file function.txt, action is write. So, okay, these are generated by the code. Likely things that as you make modifications, you probably want to have the same data in them. So what we'll do here is save these as a reference, and then sort of as you make the changes, you'll check against them. Now, I've done this code lab a number of times, and I'll tell you flat out there's some differences that do end up popping up, but they're very, very minor, like floating point differences. But typically when you're doing these things, you'll want to keep track of those kinds of changes that happen along the way. So typically what I do is just make like a reference directory, and let's go ahead and drop those text files there. So make that ref, move start.txt to ref. And then you would just do like diff on whatever gets generated later against that reference. Okay, let's start doing some coding. Now, what I like to do when I'm doing HIP stuff is just go ahead and start moving data around. Make sure I can do that. Verify that we're doing that with a profiler, and then we'll start moving some kernels around, because it's pointless to write the kernels unless you actually have the data there. Okay, it's not as straightforward as OpenMP. So in that main.f90 is where we're going to start. You see, I'm going to turn on line numbering just in case I need to reference some of these lines. Okay, so we have F, smooth F, and weights. These three allocatables, which if you remember what I said before, we need to actually, if we're going to work with these using the HipMem copy stuff, we need to make them pointers. So that will need to happen, right? But to make a lot of these functions available for us, we need to include a few more packages. So one, if we're going to use HIPFort, we're going to use HIPFort, check, and I need to make sure I have HIPFort installed. So if I don't, we're going to walk through doing that real quick. Use ISO C binding, because we're going to be using some of the stuff from this awesome package that allows us to be interoperable with C. we got HIPFort, we got HIPFort check, we got ISOC binding. We're going to, instead of using allocatables, we're going to change these 2 pointers. So let's do a search for allocatable. I was looking at parameter on the screen there. Allocatable, we're going to change that to pointer. Okay. I'm going to grab these, and then in here, what we're going to do is postfix them, or suffix them with _dev to indicate that they're on the device. Now you could do whatever you want. You could do _GPU, you could, I don't care. There is nothing that can stop you from naming things any way you want to. I just highly recommend that you use the same sort of base name as your host side pointers, and then you postfix or prefix it with some type of indicator that this is running on the GPU. This will make your life a whole lot easier when you're trying to understand what it is you're working with. Okay, so the first thing, now that we've got all this stuff set up, we've got things declared. Here I have F, smooth F, and weights are all allocated. Here's what we're going to do. We're going to start with just doing the allocation on the GPU. Okay, so we're going to call. We're going to use that fancy HIP check subroutine. We're going to do HIP malloc. What are we going to malloc? Well, we're going to malloc this fdev, smooth fdev, and weights dev. So fdev. And I'm going to use the mold argument because I don't want to write nx times ny every single time. I don't know, just for me it looks cleaner. So I'm going to take the f array, and that will be used as the mold for fdev. We're going to do the same thing for smooth f and weights. Okay, so we've got things allocated at this point. I'm going to put a freeze statement at the bottom, and then we're going to go through and make a couple changes to the make file so we can compile with HIPFort. And then, yeah, I'm going to show you how to profile, because we're going to be doing that a lot today. Yeah, let's just make sure this is all just sort of working before we get too far ahead of ourselves. So down at this deallocate, you can put it before or after, it doesn't really matter. They are their own pointers. So we're going to do call hip check again, and we're going to do hip free. This will be fdev. And we're going to do smooth fdev, and then we'll do weights dev. Okay? Alright. We've got this. We're going to take a break from this kind of coding, and we're just going to mess with the make system so that we can use the HIPFort Fortran compiler. Now, ROCm allows you to build for both AMD and NVIDIA GPUs. Even though ROCm is not supported by NVIDIA, it will work with NVIDIA GPUs. Kind of cool. So the way this works is you use the HIPFort. It's a compiler wrapper. It's really a Perl script that will determine, based on the file extension and the type of file it is, whether to use your preferred Fortran compiler or to use HIPCC. Now, HIPCC is another compiler wrapper that determines, based on the target GPU you're trying to build for, whether to use NVIDIA's NVCC compiler or AMD's HIP client compiler to build for the AMD GPUs. Of course, if you want to build for NVIDIA GPUs, you need to have the CUDA toolkit installed on your system, and you got to have an NVIDIA GPU. Well, I guess you don't need the GPU to build, but you do need to have that CUDA toolkit in order to build. So what I like to do when I'm working with make files specifically is I'll include variables that are optional, but they default to things that are they make sense. So we'll do opt roctum. Yeah, audio is distorted. I hope that's still not going on. Not quite sure what to make of that. Well, if it is, I'll redo this again next week. Okay, so what we'll do here is CUDA. We'll do user local CUDA. I'm not going to worry about it. Just going to keep on keeping on. Alright, we get HIPFort compiler. So, as I mentioned, so the HIPFort will determine whether to use the HIPCC compiler, or tell you what, let me fix the audio here real quick. It's gonna bug me. It's gonna bug me forever. Okay, let me do a quick check on this, and then we should be rocking again. All right, get that out of the way. Hopefully that's a little bit better. I'll keep an eye on the chat. Thank y'all for calling me out on that, keeping me in check here. Okay, where was I? Oh yeah, so we're gonna use the HIP-FC compiler wrapper, which will under the hood pick out a Fortran compiler for us to use. I'm gonna set this to a variable called HIPFort compiler, which will set to the user bin G Fortran. Again, default installation for like a GNU compiler installation. And then for the Fortran compiler FC, what we're gonna do is hard set this to rocm HIPFort bin HIP-FC. So let me actually make sure that's there. So we'll go opt rocm bin, oops, rock HIPFort. I do not have HIPFort, so we'll need to do that. So you get to see how to do HIPFort and make sure we don't have it any other place. No. Okay, we have AMD GPU. Okay, we'll have to install HIPFort. So we'll do that in a second here. We'll finish making this makefile, or setting this makefile up. And I'll change that path there in a second. And then the Fortran flags, we're gonna leave them where they are. The only thing we're gonna do is remove the profilings. We don't need that anymore. I'm gonna do HIPFort compiler, and then HIPFort compiler. Okay, so that should be good. Now we need to install HIP-FC. So I should have set that up beforehand, but might as well walk through this now. All right, so what we're gonna do is clone from the rocm repository. Okay, it's important that you build HIP-FC, the HIPFort stuff, using the same Fortran compiler that you're going to use to build your code. So most HPC centers will have a HIPFort installation for multiple. Yes, love it. Thank you for the confirmation there. That really helps. Most HPC centers will have different installations for HIPFort for each of the compilers that are available. So like Intel, PGI, GNU, whatever, they'll have a build for that. So we're going to build this with our G Fortran compiler. So we're going to go to HIPFort, and hopefully things haven't changed too much. Let's take a look at the CMake list here real quick, just to make sure I got my install directory or the install path correct here. Yeah, of course they do. So we're gonna do HIPFort install dir, because I'm not in I can't go root on this system from this account. So what I'm gonna do is set this CMake variable HIPFort install dir to be my home directory. So that's what we'll do. Okay, so we're gonna go to build, or we'll make a build directory. And we'll do CMake, and then dash HIPFort install dir equals home Joe HIPFort. That should do it. And it did pick that up, which is good. You should see it up there, right? The HIPFort install directory is where it should be. And let's go ahead and make. And then we'll do a make install. So at this point, we'll have HIPFort ready on here. We'll give that a minute to install. Okay, almost there. So the one thing we'll have to do after this is add to our load library path the lib stuff that's created here, so we have the HIPFort library available when we go to execute our code. Very important. Okay, make install. Great. So if I look at, I just realized I put that in the same friggin' path, of course. Yeah, so this lib, HIPFort, AMD, like we need these .a files to be available. So what we'll do is export LD library path. LD library path. You can put this in your bash RC file, or if you're a system admin, you could put this in like a profile D if you have things in a non-standard location, or of course you can use modules, which they have conveniently provided for you. Home, Joe, HIPFort, and lib. Okay. All right, now we should be good. Let me go back into that code. Samples. Fortran. And smoother source. All right, let's go back on that make file. I'm gonna go ahead and just hard code this to where I want it to go. So home, Joe, HIPFort, bin, HIPFC. Now we should be okay. All right, let's see. Fingers crossed here. Looks like we're good. So we're able to rebuild the code, no problem. At compile time, it should detect what GPU, since I have them available on the system that I'm running with. If not, I'll show you how to configure that as well, so you can pass in the GPU type that you're working with. So we got our code. Let's go ahead and run with smoother. We'll do 1,000 by 1,000 and 100. Make sure that runs, and then I'll show you. We're gonna run through the compiler, or sorry, a profiler. So we can confirm that we're actually running on the GPU, or we're allocating and deallocating our data. So first we'll do rocprof. This is the Rockum profiler, command line profile. We'll do, right now, we just need to do systrace. So we're going to create a trace profile. We will download that and view that in perfetto, so you can see a timeline of activity on the GPU. So we'll do the same parameters again. Okay, so now it's running underneath the profiler, and I'll show you what comes out of this. There's a few files that are created. They're all prefixed with this results. So hopefully the code you're working with don't have a file with the same name as some of these outputs. That would be horrible. This results.json is going to have the statistics, or the things that you need to view a timeline of activity on the GPU. So we're going to look at that in perfetto. You also have these HIP stats. This will be a hotspot profile of HIP API calls. And here you can see we've got 3 HIP malloc calls and 3 HIP free calls. For the sake of time, I'll probably reserve the trace profile here in a minute once we get the kernel up and running, okay? But here, like this file, this hotspot profile does confirm, okay, we are actually making these calls, they are happening, and here's the percentage of time spent in them. This is only comparing with other HIP API calls, right? We got the duration given in nanoseconds for those. All right, so let's get back to more coding. We know we can allocate data. Now what we're going to do is copy data to the GPU and copy data from the GPU. So to do that, we do need to understand sort of what data is updated, what is modified, etc. When we are running the smoother kernel. So if you remember, we had this smooth function oops, not that one. I wanted the gprof. Where was that gprof? Gprof
Did I save that there? Ah, I might have put it in the reference. Yep, I did. Okay, so reference, we're gonna look at gprof.text. Right, remember we're looking for this apply smoother method. So again, we're gonna grep around. Now remember, Fortran is not case sensitive, so like it's not necessarily gonna have all lowercase. So we're gonna look for that. We'll do apply smoother. And let's look in all the Fortran 90 files. Okay, so we've got a subroutine, and let's turn on line numbering. So if you do -i ignores case, -n will print out the line numbers. We've got apply smoother defined on line 89 of smoother.f90. So let's take a look in there, and we're gonna jump down to line 89. Okay, there we are. Okay, so we've got, again, there's that 2D loop I mentioned before that we would see, and then we've got our inner loop doing a reduction for this smoothf variable. So that's cool, we got that. Now what we see on the right hand side is that, of course, we look at the intent statements, right? We got intent in, so f is coming in, it's being used. Waits is coming in, it's being used, so it's sort of like read only. And then you got in out, so smoothf goes in and then it comes out as well. And we can see that just by looking at line 107 as well, like f and wait show up on the right hand side of an equal sign, so we're only doing loads, we're reading that data and using it for computation. A smoothf is being read and used for computation, but then it's also being updated, right? So there's that. We have that we're working with. We know we need to copy to the GPU before this kernel f and waits, and we need to copy smoothf to the GPU. And then on the other side, after we call it, we want to copy smoothf from the GPU back to the host because we're updating it. So we can see that, okay, so that's where it's defined. Here's where it's called, line 64 of main.f90. So that's where we're going to go put our mem copies. So we're going to, right around here, we're going to do a call. We'll do hip check. We'll do hip mem copy. So remember, we have the first argument is going to be the destination. And then the second argument is going to be the source, then the size, then the enumerator. So we get the destination. Here we're going to do fdev. The source is f. The amount of data is nx times ny. And then we have hip mem copy host to device. Okay. Now, all right, so that's really what we need to do for that. Now waits is interesting. Waits is actually not updated over and over, so it'd be kind of silly to copy it multiple times. So I'm actually just going to do that guy once up here, because f gets you know, used and reused, because you can see he shows up here. Whoops, set that numbering again on line 67. F is used again in reset f, so there could be some other stuff going on there. So I'll still want to do f dev copies in here. So here what we're going to do is, since waits is never really updated, it is pretty much read only inside of this loop. We'll just do this. And then the size, if we go back up to the declaration or the allocation here, it's going to, so we have -nw to nw. And so it passes through 0, so that's nw plus 1. Is that going to be 2 times nw plus 1 in each direction? So yeah, let's go ahead and do that. 2 times nw plus 1. Of course, if we wanted to cheat, we could just do size of. It's a nice intrinsic. Kind of like that, actually. I'm going to do that down here. It's a little bit nicer. So the size of f, right? And then down below, we can do, we're going to copy from the, actually, you know, I think we need to actually go ahead and copy the, we do need to copy smoothf to the GPU as well. So we need to do smoothf here, smoothf, and smoothf. And then after calling apply smoother, what we need to do is copy smoothf from the device to host. So we have smoothf, so the destination is now the host pointer. This one is the device pointer. And then this is going to become device to host. Okay. Whew. I think we got everything. So let's put in some comments here. So copy F and smooth F to the GPU. Copy smooth F from the GPU. All right, so we've already added a little bit of overhead because we got to cross that PCI bus a whole bunch. And as I mentioned before, it's not ideal. But we're going to do it as a start because we really just want to focus on porting one kernel. Once we port that one kernel, we'll port this next one, even though it's small. And we'll do that so that we can get these mem copies outside of these main loops, right? That's kind of what we're after here, is eventually getting to that point to where this stuff's all happening very minimally. Okay, so we got our data moved. Let's go ahead and build it and make sure it runs. Of course, it's not going to get the right answer now because we've done some extra stuff here, but let's make sure that we're actually running these things on the GPU. So there we go. Let me do the sys trace. All right. Oop, I got a HIP error code. We'll take a look at that here in a minute. Let's see what happens here. HIP error 1. Oh, wow. It's not even printing the reasons anymore. Let's take a look at what's going on here. Let's make sure we got everything done correctly. Size of smooth F. I don't know. Let's do this one at a time here. Make sure I get all these right. Okay, so that first one is causing a problem. I must have done something silly. That still works. Okay. So let's go ahead and dive back into that one. I'm gonna do hit mem copy, weights dev, weights, size of weights, That looks good, looks good. Might need to specify the device, so let's go ahead and do that. I'm going to pull up something else here so I can get that up so I don't mess that up either. Let's go in that make file. We're going to set the target architecture next, just to make sure that it's not building for something it shouldn't be. Okay, give me 1 second. Okay, so the flag that we need to use is the, it's called offload arch. So we got the HIPFort compiler. So offload arch. And then we'll set this to our GPU target, which on this system, I'm using MI50s. This is going to be GFX 906. You can use a built-in function called MyGPU. It comes with Rockem. It'll tell you what GPU you have available. But here I'm using MI50s. I know it's GFX 906. I don't have my GPU configured correctly on this system, so it actually throws a problem. But this is what we're going to use. Yeah, so let's go ahead and give that a try. So we're going to make clean. We'll make again. And let's try that one more time. Still throwing me an error code, huh? Let me take a look here. Consulting my code lab because it's a good thing I write these down. Write them down for a reason. Self data. Let's see here. So that's right. That's right. I do remember now. Okay, so what we actually need to do, and this is why the host data needs to be a Fortran pointer. Right. So this is weird. Whenever you're referencing the data in HIP mem copy, it does need to be a C pointer. That's exactly what I'm doing wrong. So you cannot pass the Fortran pointer directly into. I don't know why I was thinking that today. That's so weird. Been a long week. So what we're gonna do is use the cloc intrinsic. Let me go ahead and break this up because this is gonna start looking nasty. So we do need to convert those Fortran pointers to C pointers when you're calling the HIP mem copy API. Let's go ahead and get that in place here. Okay, maybe we're golden now. That did it. Okay. That was the trick. Okay, so when you're using the HIP mem copy stuff, that does need to be a C pointer when you're doing the mem copies. Okay, so let's go ahead and fix that in the other ones. Okay, we'll bring them back in. Okay, so cloc is what we need. And we'll do a cloc on these guys. So of course, if you just decided to declare things, and that's why I was thinking, I think the last time I had done this one, I had declared these guys all as C pointers, and it just, I think that's what did it. Anyways, this will do it. I just tidy this up. Okay, so let's cloc on this one as well. All right, now we should be good. Let's go ahead and build it. Let's go ahead and run it again, and let's do it underneath rocprof so we can take a look at what's going on. So if you remember, we had like a second for running that kernel. So like you'll see when we look at this profile, how much time is really spent. And I'm just gonna do one iteration because we don't want to spend a whole lot of time waiting for this to come back. The mem copies do eat up some time. So let's take a look at those HIP stats again. Here we go. So now we've got our HIP mem copies in there. We've got 4 of them. So we've got 3 going to, 1 coming from. So that makes sense. The total duration in nanoseconds. So if we move over 9 digits, so 1, 2, 3, 4, 5, 6, 7, 8, 9. So like 0.2 seconds spent doing mem copies. I mean, 20% of the runtime is pretty significant even for something small, right? So we'll ultimately need to get rid of that. Now we've got data to work with. Let's start offloading this dang kernel already. What we want to do, right, is start from this smoother kernel, right? This guy here. We need to write this in C, and then rather than doing all these loop iterations, we'll assign instructions to individual threads. Okay. So let me go ahead and split this. Whoops. Let's do a V split. I like that better. And here we'll make a new file, and we'll call it smoother.cpp. Okay, and at the top, of course, we'll include our HIP runtime. Okay, and then we're going to go ahead and declare our GPU kernel. So again, it's a global type specifier. Say apply smoother GPU. And then we'll go ahead and pass in our argument. So I know I have to work with F. And I had that precision stuff to worry about. So we'll figure that out here in a section. I think I'll just do, I think I have everything as floats. So we'll just worry about floats, and I'll make sure that on the CPU side, we're only working with floats. Let's do float weights. Float smooth F. Okay, and then we'll do int NW, int NX, int NY. So we've got all of our dimensions passed in by value. And then we'll go ahead and open and close curly brackets. And I'm going to use 2-dimensional block IDs. Okay. And then we also need to do something weird here because the loop indices are going to go from 1 plus NW to NX minus NW. So we'll need to calculate, how many are there and then what our starting index is. And keep in mind that we've got 1 base indexing currently used in Fortran, and we've got 0 based indexing in C. So it's a little tricky. If you don't get it right, it's just like those little annoying things that help you get the wrong answer. So what we want to do is calculate a thread ID let's just do the I dimension first. So we're going to do int I is going to be thread IDX dot X. I'm going to get that local thread ID. I'm going to do block IDX dot X times the block dim dot X. Let's go ahead and put this over multiple lines so it's easier to read. And then we're going to shift it. Right, so we want really when the thread ID is 0, we really want to be starting at the NWth entry, right? So this will be really, if I shift it to C base to the 0 base indexing, it'll be plus NW minus 1. I think I've got that right. Okay, I think in the code lab I actually might have it incorrect, which I need to fix. Okay, so we're going to do the same thing for J, but we're going to do the Y direction. Okay, but now we're going to do, thread IDX dot Y, block IDX dot Y, block dim dot Y. Okay. So we've got our I and J so that we're starting at the right spots using 0-based indexing in C. Okay. And now what I just want to make sure is that I'm not going to exceed NX minus NW or NY minus NW for J. So, and again, using that 0-based indexing, I've got if I is greater than NY minus NW minus 1 is what we want. Then we will return. So let's do that. And what the return is really going to do on the GPU is it's going to mask out that thread from doing operations. It's not like the most efficient thing you can do, but we're not really worried about efficiency right out of the gates here. We kind of just want things to work. Oops, since this should be NX, and we'll do the same thing for Y. Okay, oops. So for J, we'll do that. And then we should be good there. Okay. I suppose we could do less than or equal to, yeah, it's just whatever, doesn't matter. Little things. All right, so now we know anything beyond this point, we're dealing with threads that are going to be operating within the range we want them to. What I'm going to actually do that's a little bit different than what's shown in the code lab is I'm going to, actually no, it is in the code lab. We're going to use a local variable for accumulating on each thread, and this puts this in the registers, which is a little bit better than doing it straight out of global memory. So we'll say sm local is 0.0. We'll initialize that, and then we're going to go ahead and do our inner for loop. So we'll say for int jj is minus nw. Oh my gosh, jj less than or equal to nw. Right, jj plus plus. And we'll do the same thing in the I direction. Okay, minus nw to nw. Going to increment in the I direction. So this is just that inner accumulation loop. So if you're looking at the right hand side of the screen, the Fortran code, this is like doing the lines 104 to 110. What we're essentially doing is basically going to have each thread do its own accumulation, which is kind of nice. It just, I don't know, it's an easy way to parallelize this. Again, may not be the most efficient, but we're just going to show how this works. It's where we're starting. All right. So in C, when we pass these variables across, they are going to come across as flat 1D arrays. So you need to do your own indexing. Kind of kind of weird here, but so when a Fortran array comes across into C, the I dimension is going to vary first, and then the J dimension is going to vary second. So it's like the reverse of what you would do if you're doing 2D arrays in C. But just so keep that in mind. The way this is going to play out is we'll have, so we know we have NX values. So let's do this. Let's do this. We're going to declare some integers up here. So we'll say int IL for the element ID, and then the smoother index. So the element ID in the array is going to be the I index, which is really, when we're doing this loop, if you look at the value for F on the right hand side, so line 107, we've got I plus II, J plus JJ. So that's the index we're working with here. So you have I plus II plus J plus JJ times the number of elements in that first dimension. That's just going to be NX, right? And then down below, we've got, we're going to calculate the index for the weights, because the weights in Fortran's also a 2D index. So we're going to do ISM is going to be II plus JJ times the number of weights, right, which is, or the number of elements in that weights array, which is 2 times NW plus 1. Just remember, it goes from minus NW to NW, and it includes 0. That's where our 2 times NW plus 1 comes from. Okay, so now what we can do is SM local. We're going to accumulate on SM local. We'll do F at IL times weights at ISM. Okay. And then what we want to do is store SM local in the output. And the output here is going to be a smooth F. So we'll recalculate IL, but now just use I plus J times NX. So we're not calculating for that smoothing index anymore. And then we'll do smooth F at IL equals SM local. So each thread is going to do this operation. It's going to accumulate on its own register, and then it's going to throw that result back into the smooth F array. Okay, so that's the short end of it there. So that's our GPU kernel. Now remember, I said the other ingredient that we need is a wrapper. So I'm going to go ahead and remove that so we can just look at the C code. So we basically took that Fortran code, wrote it as if it were C, and then we broke those outer 2 loops into using the GPU threads. Nice and easy. This next part, I am going to cheat. I'm going to pull this straight out of the code lab so that I don't have to write it all, but I'll walk through very quickly what's going on here. So remember, we need to declare the wrapper as an extern C block, so name mangling does not happen when it compiles that function into a symbol in the object file. We're going to pass, now everything in Fortran is always passed by reference. So when you call a subroutine, like if I want to pass fdev, for example, as a subroutine, as an argument to a subroutine, which is going to come into the C code, it's going to be a pointer, but it's already a pointer in the Fortran code. So right, it's going to be a double pointer. So it's going to be a pointer to a C pointer, which is why on line 40 you see I've got F with that double star. So we got those pointers to a pointer. That's just how it comes across when you do this from Fortran, right? We've got the object itself as a pointer, and Fortran passes everything by reference, so it's a pointer to a pointer. So that's that. We got the apply smoother. I'm gonna call it GPU wrapper. We'll do F weights smooth F. I'm trying to be careful in keeping my arguments the same order as I did in the function. So now what we're gonna do is the calculation for the thread, for the grid and block size. So the number of threads per block, I'm actually going to use, I don't know why this is 16. You usually want to do at least one wave front on an AMD GPU, which is 64 threads, or you want to do some multiple of it. A good choice, a good starting choice, I see a lot of codes do just because, it works. For a lot of codes is 256 threads per block. Keep in mind, you can go as high as 1,024 threads per block, and you can do a whole ton of blocks. I mean, it's insane, the number of threads you can run with. So we're going to do 256 threads per block, and then I need to calculate how many blocks I need to have in order to completely step through memory. So like we already put in some guards for like whether we're stepping out of bounds here. We know the first thread is going to be it's going to be, I guess it is shifted. Ooh, I didn't account for the fact that it's shifted, so we'll figure that out here in a second. Tell you what I'll do, I'm just gonna, I think I know. What we'll do is we'll just start these off at 0, and then we'll do I is less than NW minus 1. Or I think that's what it needs to be. So it was, what was the loop size? Let's pull this open again. So we had 1 plus NW, that's what it was. So we'll make sure we're larger than NW because we're going to shift by 1. So we're going to be larger. So if we're less than NW, we don't want to do anything. And yeah, this should work. So this will make things a little bit easier just for calculating the launch parameters. You know, when you go through these like optimization steps, which we'll touch on in a future live stream, we'll start to clean this kind of stuff up. So, whoops, less than. We want this to run. Okay, so here I have NX grid cell. So now we'll just say, look, I'm gonna do 1 for every grid cell, even if it's gonna be part of a ghost value, whatever. It'll mask it out. It won't run super fast, or it'll be a little inefficient, but that's okay. So what you'll typically do is you'll take the number of points in a single dimension, you'll subtract 1, divide by the number of threads per block, and add 1. So this makes sure that you're stepping through all the elements of memory, right? And if there's a little bit over, a little bit under, the conditionals we put in will make sure that we're not stepping out of bounds. Of course, if you do end up having memory problems, you can use RockGDB to find where that's happening. There is a debugger for all of this. Okay, so here, what I'm actually going to do, so what we've done is use integers. We set, okay, 256 threads per block. We calculate the grid dimension in the X direction, grid dimension in the Y dimension. We set, here's our chevron syntax. I'm going to break this in multiple lines so we can read it. I'm not going to worry about these last 2 parameters. That'll be a topic for another day. And then we've got our arguments going in. So F, weights, smooth F, NX, NW, NX, and Y. Let's make sure it's all in the same order. That looks good. And then we've got our function all closed up nice and tidy. Okay, so we've got our kernel. We've got our kernel wrapper. Now let's define that darn interface already. There's always a question of where you put this. You know, for me, it's like if the subroutine that I'm offloading to the GPU is in a module, I'll usually define the interface in that same module. So let's go ahead and open up that smoother.f90 module. And up at the top, this is going to be above the contains statement. We're going to put in an interface. So after implicit none, but before contains. Yeah, and it looks like we're using real 32 unless I set double precision. So I think we're good. We'll just do everything in floats for now. So this won't just, tell you what, I'm just going to go ahead and delete this so no one ever does that. Everything is real 32. Great. Let's go ahead and define our interface. So we'll start with interface, then we'll do an end interface. There we go. And then we're going to do, I'm going to call the subroutine the same thing that I called it in that C++ code. You don't have to. Highly recommend it. Keeps things from being confusing. So do apply smoother GPU wrapper. We'll do fdev. Tell you what, I'm just going to call it f weights smooth f. We know this is for the device. That's okay. And x and y. Okay. Then we're going to use from ISO C binding. So I need to put use ISO C binding at the top. We're going to use the bind option here. So bind, we're going to bind a C function. Sorry, I don't think I need the quotes on C. What I needed on is the name of the method. So we have bind C, and then we'll bind it to the name apply smoother GPU wrapper. Okay, so what this is going to do is when we compile the code, we're now going to have to add a step in the make system to build the C++ code. Then when we link everything in at the end, the compiler will look for a symbol named apply smoother GPU wrapper to provide the instructions about what to do when this Fortran subroutine is called. We do need to finish defining a few things here. So we'll do end subroutine, apply smoother GPU wrapper, okay? Now, if you're using any modules inside of these subroutines, you need to redeclare them. So we'll do ISO C binding, okay, and implicit none. We got type C pointer, because all the F, weights, and smooth F are going to be C pointers by the time we get them into this kernel. So we have F, weights, and smooth F. And then the integers are all passed by value. And the way you pass things by value in Fortran is use that value specifier. So we'll do NW, NX, and Y. It's almost there, I promise. We have one thing left to do. And that literally is to call that, actually two. We got to call it in the main function, then we're going to go update our make system. So let's do this. So now I'm going to do, so we'll do apply smoother GPU wrapper instead of apply smoother. And then we'll use fdev, weights dev, and smooth fdev. We can't just use those because remember, those are Fortran pointers. We need to convert them to C pointers. We got cloc for each of these. So if you caught the video last week from doing this with OpenMP, you can already see this is a lot more work to make this happen, but totally worth it if you really want to get the extra bit of performance that you might not be able to get with OpenMP. Now, we do need to add a smoother.cpp compilation here. So what I'm going to do is I'm going to duplicate this. Cool thing about HIPFort is you can just use hipfc to compile these. I'm going to call this .cpp.o. Okay, and when it comes across the type extension CPP, it'll know to use hipcc, which is kind of nice. Okay, so let's oh yeah, now I think what we want to do is make sure that main is dependent on smoother.cpp.o. I want to put those dependencies in there. So let's clean up. Let's make. Okay, so I've got a few things that are problematic. Let's go ahead and clean that up. Oh, I'm still using reals. That's right. I took that out. It was the whole thing I was doing so you could change your precision, and it's not really necessary here. Okay, almost there. A type. Oh, I did not make that a void function. You know, that's how these things go. All right, now we're in good shape. We should be able to run, and then we'll take a look at a profile, show you how that works. All right, so we'll do smoother, 1000, 100. Let that run. Might take a little bit because of the mem copies that we're doing, but not too bad. Let's do rocprof, and this time we'll do systrace, and then we'll do stats. So stats will get us the hotspot profile, so we can see how much time we're spending in that kernel. And what I want to do is compare, just to show you that average runtime for this kernel on the GPU versus the average runtime we got before. So if we take a look at results.stats, actually let's do this. Okay, Ooh, got no kernel. Something happened there. Might not have actually run. Let's see here. So we got our copy stats. Those are all looking good. Let's see what could be going on here. We got main.f90. We're doing apply smoother GPU wrapper. F, wait, smooth F, NX, NW, NX, and Y. Let's double check everything we did. Type C pointer, F, wait, smooth F, NW, NX, and Y. That looks good. Let's check our C++ code. That looks okay. So something's going on here with that guy not running. Why would that be the case? Give me 1 second. Let me look this one up. Take a look at my code lab. Make sure I didn't mess anything up. Well, let's take a look under rockgdb. This is weird. This might be an issue with my HIPFort setup. Tell you what I'm gonna do is reschedule this live stream and we'll get HIPFort set up and I'll get you guys the solution next time we get together. Good thing is at least you should be able to take away from this a number of things you can do to prep your Fortran code to get there. These kinds of things always happen when you do stuff live. If you subscribe to this channel, you'll see an update coming up soon. I'll have the fix working for this. And of course, I'll get the code lab updated to go with it. Do appreciate you tuning in. Thanks to y'all who called out the audio issues. I'll see you guys next time.